Hey folks, I'm Mr. Rose, you should know that, and today is our COVID lesson on the remainder of heat. So last time we were in class, you saw this formula which comes straight from the MCAS sheet, this Q equals MC delta T. Remember now, Q stands for heat, and heat and energy are kind of the same thing, and by that I mean they're very much the same thing. M stood for mass. C is the specific heat. Now, specific heat is a constant for every substance. So I have down here, it would always be given to you, like the specific heat of water is 4,186 joules divided by kilograms times degrees Celsius. Or sometimes the MCAS will use grams, so it's 4.186 joules per gram times degrees Celsius or Celsius degrees. Now, the specific heat capacity means how hard or how easy it is for something to accept heat, how hard it is to heat up or to cool down. So the higher the number, the harder it is to heat up or cool down. Water, we know, is an insulator. Metals are conductors, so metals tend to have lower specific heat numbers. Then this delta T, that was just the change in temperature. Remember, temperature and heat are two different things. So we're going to practice some of those a little bit later. Right now, we're going to move on to the way we can transfer heat. Now, when heat is transferred, it's always going to go from a hot object to a cold object, no matter what. So there's a classic question. If I take an ice cube and I put an ice cube into a warm drink, does the ice cube make the drink cold, or does the drink warm and or melt the ice cube? And the answer to that is the drink always warms and melts the ice cube. Then that cold ice cube, that cold water, is now what's causing the drink to cool down. But it's transferring energy to the ice cube. Now, the way that we transfer heat or transfer energy are these three methods right here: conduction, convection, and radiation. Now, here you have a list of things that you can see. I have aluminum, glass, copper, iron, plastic, cardboard, nickel, paper, chocolate, and steel. And I want to know which one of those are good insulators and which one of those are good conductors. Hopefully, you can notice that all of these things on the list, some of them have something similar. Like all of the metals, steel, nickel, iron, copper, aluminum, those are my good conductors, which means the good insulators are all the other things: glass, plastic, cardboard, paper, chocolate, and then if I had water on there, like we just said, water would be an insulator as well. Now, we know conductors and insulators for electricity. They're also the same thing for heat and heat transfer. A good electric conductor is a good heat conductor. A bad electrical conductor is a bad heat conductor or a good insulator. So the reason why is the same. If they have easy mobile electrons, it's easy to conduct heat. If they don't have easy mobile electrons, it's not so easy, or those are good insulators. Now you might be thinking, why would I have cardboard and chocolate? Well, think to yourself, if I put those two things together, I would have something like chocolate ice cream in a cardboard container that lives in the freezer. When I take it out of the freezer, the cardboard helps it to not melt because the cardboard is an insulator. My hands, which are warm holding the cardboard tub, insulate my hand from warming up the ice cream too fast so the ice cream doesn't melt. Now here are some other things. The bottom of a saucepan, well, that's usually metal. So metal conducts heat, so I can boil my water or heat up the sauce real easy. The handle of a saucepan, that's an insulator, and that's usually a piece of plastic. Now, a quilt or a blanket, excuse me, a quilt or a blanket, that's obviously something that keeps me warm, and the reason it keeps me warm is it keeps my heat in. The blanket doesn't actually do anything if you're not underneath it, which is why sometimes if you crawled into bed with the blanket on it, the bed still seems cold. Well, once I get in, it traps all my heat. So the blanket is an insulator, and the ice cream tub we just talked about is also an insulator. Now here you have a picture of 2 feet. We have 1 foot on tile, 1 foot on wood. And I ask you can do this right now around your desk. If you put your hand on the desk, take one hand and put it on the desk, take another hand, put it on something metal. And if you're touching both of those things, you're likely to feel like the metal is colder. And the reason for that is when you touch the metal, you are transferring your heat faster to the metal than if you were touching something else, like the desk. In this case, we've all been barefoot on tile before. We've all been barefoot on wood before. And if both of those things are like in your house, they're the exact same temperature. In other words, they're at equilibrium. But when my foot touches them, I transfer heat via conduction. and we feel heat transfer. So because the tile takes my heat faster, remember, heat goes from hot to cold, and all of our bodies radiate temperature at like 95 degrees Fahrenheit. It heats up the ground, the tile, faster than the wood. The tile is a better conductor. We feel that heat transfer, and we heat up the tile faster. And we heat that tile up faster because we're touching it. We're also heating up the wood, just not as fast because, again, it's an insulator. Now, this is a little bit of an exaggeration, but we understand what I'm trying to say here. If I took a spoon and I put this spoon in hot soup, like I'm making a big Witcher's brew, look, I've got this baton here. If I am stirring with a metal stir for a real long time, energy will transfer into my metal baton, and eventually this whole metal thing is going to get hot. What's happening is I'm increasing the internal kinetic energy of the metal spoon. And what that means is I'm raising the temperature, or adding heat to it. Heat and temperature are very different things. Remember, heat is the energy it's getting. Temperature reflects that energy. So if I keep that in there, I raise the internal kinetic energy of this. I'm heating by conduction because there's direct contact, and I'm raising the temperature. You can think to yourself, have I ever heated something up so much, or have I ever seen something so hot where I can actually see it? And the answer is yes. Like if you have an electric stove, an electric oven, a toaster oven, a light bulb, all of those things heat up so much that you can actually see them heated up. Like they glow red hot in the visible light spectrum. Now, if you ever tried to change a light bulb when it goes off, it's still hot. That's radiating heat in the infrared spectrum. We can't see it anymore, but it's still really, really hot. So remember, in heat, energy transfers from particle to particle. And in those materials, right, what it says here, in those materials like metals, the mobile electrons, because they're conductors, get to heat up, they make direct contact, and we literally raise the kinetic energy of that object. The internal kinetic energy, we need to say. And so I'd like you to read this. I'm not going to read it to you. Just give it a pause. The reason why metals heat up so fast are, again, because of those mobile electrons. Every insulator, the electrons are bound tighter. So those are poor conductors or good insulators. This, you can also think like, hey, if I take a popsicle out of the freezer, the stick doesn't feel as cold as the popsicle itself. Again, because the stick is a better insulator, so it doesn't transfer my heat as well. When I put the popsicle in my mouth, or I just grab the popsicle, my hand will feel really cold because it's stealing the energy faster. So that was heating by conduction. Convection is very similar, but convection happens in a fluid. So here are some very simple questions. Why does hot air rise? Hot air rises because it is less dense than cold air. So that means that the heated particles spread out, that density spreads out, and it goes up in the air. It's kind of like buoyant. By default, that means a cold gas or a cold liquid actually does the same thing. A cold liquid, the molecules come closer together, it's more dense, so they sink down. So we know hot air rises, we know cold air sinks. This is a phenomenon that we talk about in fluids. Now, air is a fluid, so I want you to think about it like that. A fluid is just something that takes the shape of a container. And you could say, think how water is actually moving in a river. Particles actually get from point A to point B. That is actually moving fluid. It's kind of similar. I'm just trying to get you that picture in your head. Now, a radiator, like in the classroom, a radiator that generates heat, well, how does that work? When heat comes out of the radiator, that hot air rises. Well, there's air above it, and there's air above it, and there's air above it. So all of that air is getting kind of pushed out of the way. As the hot air rises, it's going to replace the air that was in front of it. And when that gets up to the ceiling, well, there's still air coming out. It's still hot air. So it's going to push that over. This generates an airflow. So I'm using my little box here. Right, the air goes up to the top of the screen, and then it's going all the way across, getting pushed. Now the air over here, now where my hand is, the air over here is still warmer, but it's getting pushed by this air, so it's at the end of the screen. It's going to fall down, and then when it's on the floor, it's going to keep getting pushed. Whoop, wrong direction. Keep getting pushed and pushed and pushed and pushed. So we can imagine this airflow, this current flow, all because hot air rises, and the air that's closest to the radiator is the hottest. That goes up. The air that's furthest away is going to get pushed down. Those are convection currents. Convection is heating by putting the entire fluid in motion. If you've ever watched water boil, you can actually see these little circular bubbles in order. They have these little circular convection currents. So we take advantage of that in refrigerators. We take advantage of that with air conditioners. It's actually how it works. If you're bored, go to www.bing.com and look up what thermal expansion is or how refrigerators work. You'll read all about it. This is a really good example of what I was just describing. Now, granted, this is a campsite, but we'll look at the left and we're going to pretend it's a beach. So I'm sure many of us have been to the beach on a hot summer day, and we know that. So like I said, we've all been to the beach on a hot summer day, and what happens to the sand? The sand gets very hot. So even though this is 7 degrees Fahrenheit, we can imagine it really, really hot. And we know that it is absorbing energy through radiation from the sun. And once something can't absorb any more energy, it releases the energy. Release, release, release. So we've touched the sand, and the sand is very, very hot. So if the sand is hot and it's releasing energy, well, that hot air is going to end up rising. Well, if I look at the picture here, 65 degrees, the water is a very good insulator. So if the water is colder than the sand, then there's going to be a cold air sinking over the water, and we're going to get what's called an onshore breeze. So we see a convection current right here. Now at night, it flips around. At night, again, easy to heat up, easy to cool down. So at night, if the sand is cold, and we've probably been on the sand before when it's not hot, the water, on the other hand, does not lose as much energy or does not radiate as much heat because, again, the water is a good insulator. So now I have hot air rising over here. We've got cold air sinking over the land, and we get an offshore breeze. Now, this is a phenomenon that really happens. If you've ever spent all day at the beach, you may have noticed it before. If you know anybody that surfs, it's the same thing. They'll tell you the same thing, that in the morning you get an onshore breeze, just like in the picture. Now, the last form of heating is by radiation. Let me just go one more time back to convection. Remember, conduction is heating by contact and literally raising the internal kinetic energy of the object, while, convection is putting the whole fluid in motion. If you've ever seen a lava lamp, the lava bubbles up and down, and that's also a convection current. The last one should be the easiest one for us. It's radiation. Here's my physics joke, ha ha ha, because here we got Santa Claus, here we got the reindeer, and you can see Frosty the Snowman, who melted because of electromagnetic radiation, or was heated up by the sun. So radiation is literally heat energy. It is heat energy that is carried in electromagnetic waves. We know all about the electromagnetic spectrum. Here are some examples. That should say visible light, microwaves, radio waves, X-rays, gamma waves, infrared, ultraviolet, and here is a picture of transverse waves, which we're pretending are electromagnetic waves. Now, every single object emits electromagnetic waves, no matter what. We emit electromagnetic radiation in the form of heat. Every object emits electromagnetic radiation, most of them in the infrared spectrum. But like I said earlier, if you ever turn on an electric stove, you can see it glowing red hot. That's in the visible light spectrum. Now, the interior of a car is a really good example. How does that work? I'm going to take a second for you to read this. Hopefully you paused it and read it. Now let's look at this picture. So here I've got the sun, and there's glass in the windshield. Now, the glass does a lot of things. Remember, we talked about opaque and transparent. The glass is transparent to visible light, but opaque to ultraviolet and infrared light. So all of that visible light is coming down through the windshield into the car. Well, the seats can absorb that energy. Remember, it's energy, just energy. So the seats get hot, and the seats get hot. You probably sat on a hot seat in the summer. Well, once the car absorbs all that energy, the seats rather, just like the sand on the beach example, the seats can't absorb anymore, so they let all that energy go. They let energy go, they let energy go, they let energy go. And they're letting energy go in the infrared spectrum. Well, just like the windshield that keeps some of that stuff out, it's opaque, it's going to keep that stuff in now. So it's just radiating but it can't get out anywhere. So that heat just stays in the car. When you open the door, you get hit with that wave of hot air. So it's literally kind of making a solar oven just in the car. All that is because of electromagnetic radiation. So, things that we need to know, and this kind of makes sense. If something absorbs a lot of energy, that means it reflects very little. So, like my shirt is black, that absorbs a lot of electromagnetic radiation. It also releases about it. A mirror, on the other hand, is the opposite. If I hold a mirror up to the sun, it's just going to reflect all that energy away. So a good absorber is a good emitter. A poor absorber, that means it reflects energy. So something that does not absorb a lot of energy does not give off a lot of energy. All right, so now here are some examples. I want to say we've got a pot of water here, and how exactly is, let's see, a saucepan is partially filled with water, and there's an X right there. We want to explain how heat is transferred from the hot plate to the base of the saucepan. Now, before you listen to my explanations, I recommend pausing it, seeing if you have your own explanation. Now, how is energy transferred to the saucepan? Well, the hot plate is touching the metal pan. Notice that's a different thing. That looks like it's a plastic handle. That's an insulator, so I don't burn myself. And since it's touching, it is heating up the pot by conduction, which means it is literally raising the internal kinetic energy of the pot. Now explain how heat is transferred from the base of the saucepan to all of the water. Since saying all of the water, you can really say two things here. One is a better answer. The water that is in direct contact with the pan, that might be conduction, but it's not staying there. As soon as it heats up, it starts to move. And when that water is moving, that's convection. So the hottest water that's right there goes up. It takes the place of some of the cooler water, which comes down. And we get convection, which is why all of the water gets hot. The last, explain how heat is transferred from the hot water to the air at point X. Well, we do have two things going on. If you say something like steam, steam is just more convection. But even before the steam happens, if I just put my hand over the pot before it's steaming, I would feel it warm. Well, that water is radiating energy in the form of electromagnetic radiation. It's infrared heat, so I'd be heating up that X by radiation. Now, this is a weird picture, but this is a picture that represents a basement, the first floor, the second floor, and this is a radiator that's on the floor of the first floor and the floor on the second floor. So, give an example of where heat convection occurs in this system. Again, I recommend pausing before you hear my voice. So, convection would be, well, you see the fire. The fire is definitely radiation, but it's heating up all this water. And then the hot water is rising and then going to the pipes. So the hot water rising and replacing this cold water, a colder water sinking, that is convection. So I could say convection's happening either in the water tank and or in the water tank and in all of the pipes. Give an example where radiation occurs in the system. Hey, they even give you a hint with all those squiggly lines, those electromagnetic radiation, infrared heat. So radiation occurs above the radiator, above the heating system. We get heat coming from the pipes. What purpose does the ceiling fan help heating the home? Well, since hot air rises, the ceiling fan circulates the air and helps with a convection current, helps push all of the hot air around so it doesn't just sit on the top of the ceiling. Explain why the pipes carrying the hot water run along the floors instead of the ceiling. Well, they run along the floors because we know hot air rises because hot air is less dense than cold air. So if I heated up the air and it was already at the top, it would just stay at the ceiling. That is the majority of the information. The very last bit I'll go through kind of fast. It is change of phase. We know we started this lesson a couple of days ago with 3 different phases: solid, liquid, and gas. Well, it takes energy to change all of those substances. In other words, when a substance changes phase, it takes a lot of energy to do that. So this is a really good picture, and the easiest way we can think about this is if I'm holding an ice cube in my hand, I am 98.6 degrees Fahrenheit. If I hold an ice cube in my hand, I'm going to melt that ice cube, which means heat or energy goes from hot to cold. I am literally adding water to the ice cube such that I'm melting the ice cube. The ice is going from solid, absorbing my energy, to liquid. Now, obviously, my hand is not warm enough to make water vapor, but then if I took that water that I just melted from the ice cube, put it on the stove so there's a fire and it started to boil into water vapor or steam, that's adding energy because it's on the stove. So to go from a solid to a liquid to a gas is adding energy, or the object has to absorb energy. To go the other way around, to go from water vapor, which we see over here, to liquid water, all the way to solid water, which is ice, that requires releasing energy because water vapor has more energy. So where have you seen that before? You've seen that before with like a cold liquid. So if this was a cold glass on a hot day, all of a sudden I could make water. There might be water droplets on the outside of my glass, condensation. Well, how does that happen? Heat travels from hot to cold. If this was a cold substance, I would be transferring energy from the air into my liquid, warming it up. Well, the water vapor in the air is going to lose energy and end up with little water droplets on the outside of my cup. So condensation is an example of losing energy, going from water vapor to liquid water. It is losing or releasing energy to the system. So evaporation goes from a liquid to a gas, requires energy. It absorbs energy. Condensation goes from gas to liquid. That's giving off heat, or that gives off energy. Boiling is a case of evaporation, and water boils at 100 degrees Celsius. Again, I'd like you to read all these notes if you would. This is the same thing, or just more of an example. I'm just moving forward to get to a heating curve. Sublimation is some special thing. Sublimation is like liquid nitrogen, where it goes, or not liquid nitrogen, I apologize. Well, dry ice. If you've ever seen dry ice, it goes from solid right to gas. It skips one of the phases of matter. All right, this is what I was looking at. This is a heating curve for water. This would be freezing. Oh, it's actually not for water. Oh, it could be for water. It is for water. It says ice could be super cold, gets to 0 degrees. 0 degrees is when ice changes to liquid. This spot right here is a flat line where I'm adding energy to the system but not changing phase. Then all of a sudden I go from water boiling, starting to boil. Now at 100 degrees it's boiling, and now it's changing phases all the way at 100 degrees. This line right here, I'm still adding energy. Look at all this. All the heat added, heat added, heat added. We're adding energy until it becomes steam. This graph shows you why you can actually burn yourself more with steam than with boiling water, because steam has more energy. Look how much energy I added to that. Now remember, it always takes extra energy to change phases. Now, that's all I have for this video. I know it was very long. I'm going to have another video with some examples that'll be much shorter. I recommend you pausing and you trying the examples yourself. I will say that, I will type that, a whole bunch of reasons. By all means, if you have any questions, please send me an email. Thanks so much. I'll see you folks soon. Good luck on the MCAS.